Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. I am enthusiastic about this one. This is one of my favorite sections in all of Calc 3. I promised at the beginning of these Chapter 16 videos that by the end of it we were going to do some weird stuff, and we have arrived. The weird stuff is upon us. Not immediately, though. We're gonna build up to the weird stuff. Even within this series of videos on this 16.5 section, we're gonna build up to it. Section 16.5 is it's a continuation of 16.4. It's like a cross between 16.4 and 16.3, essentially. So in the first half of chapter 16, we learned about double integrals, and then in 16.3, we learned how to do double integrals in polar coordinates when we had round things. And then we learned triple integrals, and now we're going to do triple integrals in round coordinate systems. So things are going to get a little weird at the end because of the round coordinate systems are going to get a little goofy. But first, I should clarify. There are two different round coordinate systems. In 2 dimensions, you only have the one. In 2 dimensions, you're either working with rectangular coordinate systems, you have your x-axis, your y-axis, that's it, you're done. Or you have polar coordinates where you have an angle that goes around and then a radius that gives you a distance at that angle. So there's only those two. We can do x's and y's, or we can do r's and thetas. In 2 dimensions, that's all you get. In 3 dimensions, we still have rectangular stuff. We've done that. That's your x's and your y's. There are 2 different ways we can make our coordinate system round if we're working in 3 dimensions. And one of them is going to make a lot of intuitive sense, and that's the one that we're going to start with. It's called cylindrical coordinates. And cylindrical coordinates are basically just, you take polar coordinates on the xy plane, so you have an r and a theta, and then to move above or below the xy plane, you just have a z-axis, and that's it. That's your coordinate system. It's polar plus a z. The other way we're going to do round coordinate systems in 3 dimensions is called spherical coordinates. And spherical coordinates is a lot less intuitive. In spherical coordinates, you have 2 angles and a distance. So you still have a theta angle. So for now, we're going to pretend like this horizontal is the xy plane, and that the z-axis goes up, down, above this horizontal. So the angle theta works just like it did in polar coordinates. In polar, the angle theta will rotate you to the left and to the right on the xy plane. This is sort of like, I like to think of spherical coordinates sort of like some sort of artillery cannon. You have one device that's going to rotate this thing to the east or west. I should stick with left and right. You have some device that's going to rotate this thing to the left and right, and that's theta. You have another thing, it's either going to aim your cannon upwards or aim your cannon downwards. This is your other angle. This second angle is called phi, or phi. I think I usually hear people say phi, but I think we pronounce that wrong. I think it's supposed to be phi, P-H-I. But anyway, once you've settled on a left and right orientation with theta, then you have the second angle that will move you up or down, depending on what angle you want to sort of launch this thing at. And then you have a distance. Your third coordinate is called, we don't use r in an effort to distinguish spherical coordinates from cylindrical coordinates. We use sort of the Greek version of it, which looks like a P, but is pronounced rho. And that's going to be like your distance. So We have a left and right angle, we have an up and down angle, and then we have a distance. And it's called spherical because if you fix rho at a certain distance, like distance of 3 or whatever, and then you let your phi sort of rotate between all the different possibilities for phi, and you let theta rotate between all the different possibilities for theta, it makes a sphere. So that's what we're going to be talking about today. That is my vague body motion interpretive dance version of what we're going to do with spherical coordinates and cylindrical coordinates. I'm going to talk more about them while also writing things down for you to see when we get to them, but I'm going to do that like separately in pieces. We're going to start with cylindrical coordinates, and we're going to do a lot with cylindrical coordinates, and then we'll get to spherical coordinates and we'll talk about those. I just wanted to give you a little preview of what's coming. So let's start with cylindrical coordinates. I want to sort of diagram some cylindrical coordinate stuff. If this is x and this is y and this is z, this angle is still theta. That hasn't changed from polar. This distance is still r, and then this will give you a point on the xy plane. And then above that, you'll have a z coordinate. So this will give you your x, y, z coordinates. We're just using r and theta to sort of get around the xy plane. And this one is called cylindrical because if you fix an r value, like if you fix r at 3 and then you let theta do whatever it wants, that'll take you in a full circle and it'll give you a circle on the xy plane. And then if you also let z vary between whatever it wants, that gives you a cylinder. And a cylinder, I think a cylinder is the perfect word to describe these coordinates because along two of these dimensions, along the x and y dimension, it's round. It's doing circular round things. And on the third dimension, it is just perpendicular to those first two. So you're not getting spheres. It's only round on two of these dimensions. And then it's perpendicular on the third dimension. It's like a soup can. It goes up and down perpendicular to your circles. It makes this cylinder. So I guess we should talk about this. X, just like in polar coordinates, x is our cosine theta, y is our sine theta. Z, you may be surprised to discover, is z. And of course we still have x squared plus y squared equals r squared. These are sort of the basic conversions we're going to use in cylindrical coordinates. With that in mind, I want to do a triple integral in cylindrical coordinates. So, I want to do the integral. I want this to be a volume, so I'm going to integrate the function 1. I want to integrate a cone. So I want z to go from 0 to 6 minus the square root of x squared plus y squared. I want x to go from negative square root 36 minus y squared to positive square root 36 minus y squared. And I want y to go from negative 6 to 6. In rectangular coordinates, this thing is a kind of a terrifying mess. There's a lot of square roots of things being squared. If we tried to integrate these things, we would need to use inside, outside, other integration techniques, and there's not any other for us to use, so I think we would end up, if we did want to integrate these things, I think we would have to end up using trig substitution, and we would get arc signs all over the place, and then they probably wouldn't be nice arc signs. We'd probably have to use the half angle formula by the end of it. The whole thing would turn into a catastrophic mess. But we know that this is a cone. This is a cone above the xy plane. Starts on the z-axis. It starts at a height of 6. As this square root of x squared plus y squared, we know that that's just r. So as r increases, this thing decreases linearly. That's what makes it a cone. And it goes out to a circle of radius 6 on x and y. So we can pretty easily transform this thing into a triple integral in cylindrical coordinates. Z is going to stay the same. X's and Y's are going to transform into R's and thetas, and we'll see whether or not that looks better. So I'm going to set it up as a triple integral. I'm still integrating 1. I'm going to have a dz. That part's not going to change. I need to transform the dx and the dy. And this transformation is going to work exactly like it did in polar coordinates. Dx dy is going to become r dr d theta. Which means I need to put an r here for me to integrate. And then dr d theta over here. So this is now, I'm not just integrating the function 1 anymore. Now I'm integrating 1r. Z is going to go from 0. That part's not going to change. I'm going to go, instead of expressing this cone shape in terms of x's and y's and weird square roots, I'm going to express this as 6 minus r. Because the square root of x squared plus y squared is just r, and that's a very convenient transformation. R is going to go from 0 to 6, and theta is going to go from 0 to 2 pi to give me that whole circle. Not so bad, all in all. And now, we can start integrating. The integral of r is, this is going to stay the same, 0 to 2 pi here, 0 to 6 here. The integral of r is r squared over 2. We're evaluating this at 0 and 6 minus r dr d theta. Oh, no, I'm sorry. I did it wrong. We're not integrating r. Well, we are. We're integrating r, but on z. So this is at just z r. 0, 6 minus r. This is z equals r equals theta equals theta r z dr d theta. Okay, so forgive me, I integrated on the wrong variable. the integral of r dz is rz. And then we evaluate this. I'm going to bring it over here. We still have, that's going to need to be bigger. You still have the integral from theta equals 0 to theta equals 2 pi. You still have the integral from r equals 0 to r equals 6. In here, we have our z as a function of r and theta. So z is 6 minus r, that's our function. And then we have r dr d theta. And I want to pause here so I can talk about what this is. This is our z equals a function of r and theta. This thing we have right here is exactly what we were doing in section 16.3. This is us integrating, doing a double integral in polar coordinates of a function to find the volume under that function and above the xy plane. So I'm not even going to finish it. We already know how to finish this. We know how the story ends. We've done this before. I want to make the connection here that sometimes triple integrals in cylindrical coordinates will just immediately collapse themselves into double integrals in polar coordinates. This is going to happen not all the time, but it is going to happen a lot. Where we've done this double integral in polar coordinates. We put a function of z here. We do r dr d theta. We do the double integral. We know how to do this. We've done it before. Adding the third integral where we do a dz, and we just plug the function in for z here. After that integral, it's gonna work out the same many times. So if this is functionally just the same as a double integral in polar coordinates, which we already know how to do, why are we doing it? And there's a couple reasons. Just like when we talked about triple integrals in 16.4, the reasons are largely the same as the reasons we had in that section for expanding into triple integrals. The first reason is that this only happens when you want a volume. And so if you're integrating the function 1, then you're looking for a volume. And then you'll get this same sort of thing, usually. If you want something that's not a volume, like if you want to actually integrate a function in here, like a density function or just some weird function so you can experiment mathematically with what happens in this integral, you can do that using a triple integral. You cannot do that using a double integral. So that's advantage number 1. So we can integrate actual functions in here instead of just the function 1 to get a volume. We can put functions in there and do the triple integral that way. The other reason that we would do this is this only collapses into a double integral in polar coordinates when the bounds on z start at 0 and go up to a function. Hopefully you remember from the homework in section 16.3 that there were a lot of these like island problems where they would contrive like a weird shape like e to the negative x squared plus y, or e to the negative x squared minus y squared, something like that. And then they wanted you to find the volume of the non-negative part of it. And that shape by itself was never non-negative. So these functions always had like a e to the negative x squared plus y squared minus 2. So they were taking this entire shape and they were sinking it 2 units down so that part of it was negative, and that's how they were getting this volume. We don't really have to do that here. We can do goofy bounds if you're using a triple integral. We don't have to take these things and sync them by 2 so that we're definitely going to the xy plane. If you want, you can cut it off wherever you want with whatever radius you want. You can start at weird z values. You can find the volume between two different z surfaces. So we can mess with the bounds a lot with a triple integral. We have a lot more freedom to play with here. We don't have to contrive weird half-sunken islands to find the volumes of. And we can do densities. Those are the two big advantages we have for triple integrals. I'm at 20 minutes, so I'm going to cut this video right here. I really am not going to finish this. You know how to finish this. I'm going to start the next video talking about some other more exciting examples, so stay tuned.